All right, in this video, I'm going to be looking at just section 3.3, and really 3.3 through 3.7, 3.3 through 3.5, together with 3.7, are looking at some rules for finding derivatives. That enable you to avoid some of the complicated algebra that you have to do when you're using the definition of a derivative. So these are some rules that we can use rather than using the definition of a derivative, which involves the difference quotient. Okay, so 3.3 really gets at some of the basics. Okay, for one, it says if your function is just some constant, then the derivative of that function is 0. All right, then there's one that says if your function is a power function, x raised to some power, then the derivative of that function can be found by putting the exponent down in front, x raised to the n minus 1 power. This is what we would get if we had used the difference quotient, but we just don't have to. Okay. All right, then putting a constant in front of a function. So if you have like, say, h of x equals some constant times your function, times a function. So like that. You can figure out what h prime of x is. Let's say it this way. Then h prime of x can be found by pulling the constant out in front and just doing the derivative of f. Okay. So that's what you do when you have a constant multiple. Okay, let's see. Oh, another one was this. If h of x was actually the sum of two functions, then when you go to do the derivative, it's okay to do the derivative of each piece. But by now we've also talked about, and then add them. By now we've talked about the product rule, and we know that that's not the case. Okay, so note, it's not the case. If that's times, you can't just do the derivative of each piece and multiply. Okay. If h of x equals f of x times g of x, then h prime of x does not equal f prime of x times g prime of x. Okay, so that's a big thing to watch out for. Okay, that's what we learn. We learn how to do that in 3.4. Okay, so don't misinterpret it. Okay, don't use it when you can't. One other thing in 3.3 is how to do the derivative. Oops, let me get back just a minute. Here I was. Okay, is this one. If h of x equals e to the x, then h prime of x, believe it or not, equals e to the x. It's a very unusual situation. That's why having functions in terms, exponential functions written in terms of that base e, it's really good. And remember, e is just a number, okay? That's a little less than 3. So this is basically 3 to the x, but most exponential functions don't turn out to be exactly equal to themselves. But e to the x, the derivative of e to the x is e to the x, okay? So those are the things we did. So this is the constant rule. This is the power rule. This is the constant multiple rule. This is the sum rule, and then this is how you get the derivative of an exponential function. Okay, so now I'm going to go to the 3-3 homework, and do a few examples. Okay, so let me see. Let's do number 8. I'm just going to kind of pick a few of them off of there to help you. So here's number 8 from the homework. It said g of t equals 4 square root of t. So this is why we reviewed some stuff on exponents, because I'd like to see that as a power function. Oh, and by the way, the power rule in 3-3 didn't start off being defined for just any n, but then eventually it was. So we're going to use it in this case. It just doesn't look like it yet. So what I want you to remember is that square root of t is really t to the 1/2 power. Okay. See if I can figure out the best way to have this pen. Okay. All right. So that's g. Let me write it right here, actually, so I save a little room. And remember that the 1/2 is really only on the t. And that's what that says, or you can emphasize it by doing that. All right, so now if I want to do g prime of that, then what I can do is I can pull the 4 out in front and then just do the derivative of this piece. So there's the 4. And then when I do the derivative of that piece, I'm going to bring the exponent down, multiply by t raised to the 1/2 minus 1. Okay, so that's what I'm doing. Then I'm simplifying these two. 4 times 1/2 is 2. 1/2 minus 1 is negative 1/2. Okay, and that would be your answer. Okay, so much easier than this. This is what we would have done in 3-2. We would have done and found the limit as t goes to, as h goes to 0, not t, as h goes to 0. Okay, and we would have had to do some conjugate on top and all of that mess. Now we have this easier way of doing it. Okay, now that I'm going to not stop there on this one. Okay, I'm going to go and simplify it a little bit more because of the negative exponent, but it really turned out to be 2t to the negative 1/2. There's one more thing. Since it started with a radical, it's best practice to go ahead and get the radical back in there. And so there's where you have to also remember that that exponent being negative means that that part right there is going to be 1 over the square root of t. Now the 2 is just to the first power. So leave the 2 where it is, but then you can take the t to the negative 1/2. That's 1 over t to the 1/2. And so it turns out to be 2 over the square root of t. Okay, so that's number 8. All right, so let's see. Let's look at number 10. That's one that allows us to get at a couple of the issues. All right, so with number 10, you've got almost a polynomial. They want you to find the derivative of this function. F of x equals 10x to the 4th minus 32x plus e to the 5th. Okay, so we got the sum and difference of stuff. So that sum rule that we were talking about right here, that also is true if it's a minus. It's also true if you have more than just 2 terms. So if I need to do the derivative and I've got terms with pluses or minuses, then I can just do the derivative of each piece. So now this, I can use the power rule. This would be 440x to the 3rd. Bring the 4 down and multiply, and then take 1 away from your exponent. This one would be minus 32. It's like that's to the first power. So that would be minus 32x to the 0, and x to the 0 would be a 1. So that's why that's just minus 32. And then don't think that the derivative of e to the 5th is e to the 5th. The derivative of e to the x, if f of x were e to the x, the derivative would, I can't even read that. Okay, let me say what I'm trying to say again. Let me see if I can get this to right. If your function were e to the x, then the derivative would still be e to the x. You should not have an e to the fifth on this one because the derivative of this piece would be 0 because it's a constant, e to a set number, and the derivative of a constant should be 0. So your answer should just be 40x to the third minus 30 minus 32 on that one. On this one, I would go that far. Okay. All right, let's see. All right. Okay, then sometimes, you know, if all we had were these rules, if we had one like, let's look at these three. I'm not going to necessarily finish them, but just to show you the gist of what they're getting at. Here, then there's 3 questions where you might have to do some algebra in order to use the rules that they talked about. So like there's 13 had a problem like this, 6x squared plus 5. Okay, 14 had a quotient. Okay, and 15 had an exponent on this. Okay, all right, now because these are in section 3.3, we haven't talked about the product rule. If we had, you could use the product rule here. Okay. We haven't talked about the quotient rule yet. That's in 3.4. If we had, you could have used the quotient rule on 14. And on 15, that would be one where we could use the chain rule. Those are all coming later. Okay. So what they intend for you to do here is to go ahead and multiply the 5x plus 6 times the 6x squared plus 5. And you ought to remember FOIL. So you're going to wind up with a 30x to the third. Let me get it in descending order as I go. Plus 36x squared plus 25x plus 30. So that's still f of x. But now I've got it changed into a polynomial. So I can just do the derivative of each piece. So this would be 90x squared plus 72x. You know, bring the exponent down and multiply, and then take 1 away from the exponent, plus 25, and then the derivative of this would be 0. Okay, and so you'd wind up with the derivative, first derivative being that. By the way, later in the section, you do second, third derivatives, and all you do is keep that process up. Okay, so on 13, that would be your answer. Okay. All right, then on 14, right now, you would have to do some algebra to be able to do it because you don't know the quotient rule yet. So what you would do is just remember that x to the 8th, that this is the same as 4x to the 8th over 5x minus 3x over 5x. So you can knock out the x there. This first term would become 4/5 x to the 7th minus 3/5 for the second term. And then from there, you can do the derivative. Okay. All right, and then on 15, what you'd have to do, since you don't know the chain rule yet, is you'd have to think about that being 7x plus 2 times itself. And then you can FOIL it and get 49x squared plus 28x plus 4 eventually. And that's still f, but now it's just like this problem. And you just like this problem here. So now you just use the power rule for each of the different terms. Okay. All right, so that's kind of the point of 13, 14, and 15. I think you'll be okay with those. Okay, I think I'll do 15 just to kind of give you a preview because we're going to do the chain rule in a later video. So for 15, after you did that multiplying, you would use this same idea. So you do 2 times 49, so that'd be 98x, plus 28, and then the derivative of the last piece would be 0. So that would be f prime of x, okay? And then in 3.7, we learn the chain rule. And we've already talked about it, so let me kind of relate that back to this problem, which would allow you on this one to do this. Okay? So if you needed f prime of x, you'd bring the exponent down, times that, raised to just the first power, but then you'd multiply that by 7. Okay? So you'd wind up with 2 times 7 is 14 times this. And notice that turns out to be 98x plus 28. So the chain rule we learn later says you can identify your inside and outside functions and then do the derivative. Derivative of the outside function, and then the derivative of the inside. It's right there. And they turn out to be the same. Okay, and that happens in 3.7. And then the product rule, this could have been done using the product rule. That's in 3.4. This could have been done using the quotient rule, and that's in 3.5. But really, if it's easy to multiply, if it's easy to simplify, you might consider doing that. Okay. All right, let's see. All right, here's one that I thought you might have trouble with because it involves e's, and you might not remember a lot about that from pre-cal. So number 17 said, find the equation of the tangent line at x equals a. So here's your function. And x, a, they want you to use is ln of 12. And they're picking ln on purpose because it's the inverse of the e function. So it'll help you when you go to evaluate it. So it said, find an equation of the tangent line at this number right here. Okay, so first we want the derivative, which happens to be the same because this is an e function. So the derivative of the function would still be e to the x. That doesn't happen on any others. Okay. Then I want to know, eventually I need the equation of the tangent line. So what I'm going to do now, remember derivative is really slope. So this is the formula for the slope of the tangent line anywhere. So now if we want to know what it is when a is that, we're just going to plug in ln of 12. So that's going to give us the slope of the tangent line at 12. So that's the slope of the tangent line at 12. Okay. I don't want to write that. I just want that to be in there. Okay, now the thing about e and ln is they're inverse of one another. Okay, so that's going to equal 12 because they would undo each other. You can do it on your calculator. Just look for the e and the ln buttons. So that's the slope of my tangent line at 12. So I'm going to put that. It wants the equation of the tangent line. So that means I'm going to use this formula. Okay, I'm going to be putting 12 there. I'm going to be using ln of 12 for my particular x value. So that's going to go right here. And then I just need to do the plug in the ln 12 into this. And it just happens to be the same as the slope. So it's a little confusing because usually these are different, but this is a really unusual case. So here I'm trying to do y prime evaluated at a particular spot, and I got e to the ln 12, and that equals 12, okay? But then in order to find the y value associated with an x value of ln 12, I'm actually plugging in to y, and I'm evaluating it. I'm evaluating that function at ln 12. It just happens to also be 12, okay? So y minus 12 equals 12 times x minus ln of 12. Okay, so then I'm just going to distribute and add 12. Okay. And a lot of times there's not a whole lot you can do to simplify that, because that's, if you did try to like plug something in to it, it would turn out to be a decimal, and you really don't want to be rounding things off. Okay, so this was number 17. Okay, I did it because it involved the e's, but it's kind of unusual. So we got 12x minus the 12 ln 12 and then plus 12. Okay, and so the gist of it is this. Okay, here's the y function. Here's what y equals e to the x looks like. Okay, and then it's that somewhere, wherever ln 12 is, and I didn't look up, I don't have my calculator right here to evaluate what ln of 12 would be, but you're coming over to an x value of ln 12, and what you just found right here is that the slope right there, at that tangent line, the slope of that line right there is 12. Okay. Okay, that's 17. All right, then let's look at, say, number 19. Okay, number 19 gives you a function. This one has a radical in it. And in part A, we want to know, find all the points at which the tangent line is horizontal. Find all the points where the tangent line is horizontal. Okay, and on part B, find all the points where the tangent line has a slope of -1/2. Okay. All right. So first off, to be horizontal, the slope would have to equal 0. Okay. So that you have a line that's horizontal. All right. So what we're going to do is we're going to start with our f of x, and let's rewrite that to be x to the 1/2 power, so we can use the power rule to do the derivative. So we need the derivative to get the slope of the tangent line. So this will be the formula. So bring the 1/2 down, multiply by 30, you'd get 15. Take 1 away from 1/2, that'd be -1/2. And then that's the derivative of this piece. The derivative of this would be -3. Okay. Now, that's the derivative anywhere. Okay. You want to know which of these x values would cause this whole thing to equal 0 on part A, and what are the x's that would cause this whole thing to equal -1/2 is what you want to know for B. So on A, you're going to solve this. Okay, and on B, you're going to be solving this. So don't set the original function equal to those numbers. Make sure you take the derivative first. Okay, and you might, we maybe should have gone ahead and switched it back. Remember, the 15 isn't to the negative power, so it stays where it is. So that's what you've really got. So you might want to switch it back when you're trying to solve it. That might help you in the solving process. So, okay, so this is what I'm trying to solve. So one thing I could do is add 3. That would get me to here. And then at this point, I could multiply both sides by the square root of x, which would give me a 15 equals 3 square root of x. Okay. Then I could divide by 3, which would give me that the square root of x would equal 5. And I just moved it so the square root of x was on the left. So now I'm going to square both sides. and I get that x would equal 25. Now there's a chance that that could lead to an extraneous solution, so you really should double check, but that's fine. When you plug in a 25 right here, you'd get square root of that is 5, you'd get 3, 3 minus 3 is 0, so that would be just fine, okay? So you wanted to know what was the x that would wind up causing the slope of the tangent line to be, or the tangent line to be horizontal, the slope to be 0. It would be having an x of 25 that would make that happen. Okay, so that's the first part of number 19. The second part is going to be just for you to then do the same thing, but put it equal to -1/2. So let's see, we're going to go in here, and you might first change it to the radical if you hadn't already. Okay, and then one of the things that I do a lot of times I would use here would be to multiply through by 2 square root of x everywhere, because I am allowed to since it's an equal sign, and then that would knock out that denominator, knock out that denominator. So that would give me a 30. That would be minus 6 square root of x. And then over here, minus the square root of x equals a negative square root of x. Okay, then I might add the 6 square root of x to both sides so that I get my number isolated. And on the other side, that would now become 5 square root of x. Divide by the 5, and you'd get that the square root of x is 6, and so x would equal, you have to square both sides, so x would equal 36. And 36 doesn't cause you to get anything undefined, so that should be okay. Now let me read the question precisely. It says, find all points on the graph at which it's horizontal. So it's horizontal at an x equal 25, but if they want me to find the point where that happens, then I need to find the y coordinate of that. Same thing over here. I know the x, I need to find the y, and you need to be careful because I don't plug in 25 into the derivative. Go back to your f of x. So f of x was this. You want to find the point. Find the point. I didn't really write that clearly. Where the tangent was 0. Then you need to find the y coordinate. So make sure you don't go to f prime of x. Go back to f, plug in the 25, and work it out. So you wind up getting 30 times 5 minus 75. So that's 150 minus 75, which is 75. Okay. And to find the y coordinate of that, we'll do the same thing, but we'll plug in 36. Okay, so that's 30 times 6, which is 180. And 3 times 36 is 108. So that would be 72. So that would go in there for the y. Okay. All right, so that was problem number 19 worked out completely. And it's just that at the end, you really don't just want to know what were the x's where that happened. That's these two. You wanted to know what were the points where that happened. And you could sometimes get more than one point as well. Okay. All right, and then let's see. Sometimes you might be asked to do a derivative to a higher order. It's not a really good example of that. I think you'll be fine on that. Okay, so if they want you to do like f double prime or the third derivative, you would just keep repeating the process. Okay. All right, so I think that kind of gives you a good overview of 3.3 and with a few examples worked out. So let me stop that and get it posted.